think audio is unmute, video is recording. Yeah. So, welcome everyone. So, this is the first lecture on the topic of heat transfer. Specifically, today we'll be talking about 1D heat conduction and that too steady state and primarily through plain walls or rectangular bricks, that kind of stuff. Next class or next week, we'll discuss about the cylindrical uh, pipes and tubes, that type of heat conduction problems. Uh, so, before going to the problem solving, some basic things about the uh, heat conduction equations or in general heat conduction. Uh, so, there are, this was discussed in class also by professor, but there are two modes through which heat conduction takes place in solids usually. Uh, one is through free electrons. That is typically a case in uh, metals, normal metals or liquid metals, etc. And then there is heat transfer through uh, lattice vibrational modes of energy transfer. So that is the case in something like diamond. So uh, based on that, first of all, we have so from there actually this heat conduction is basically phenomena in which heat is diffused through the intermolecular or interstitial, whatever you want to call it, but it's a diffusion dominated process, and that's why it's slow. Whereas we'll talk about convection, etc. later, radiation convection. So convection is mostly uh, momentum transfer is there, so it's not a diffusion dominated process, it's inertia dominated, and that's why it's faster. In case of there are also various cases, we'll talk about those later. And radiation is a different topic altogether, so we'll deal with it when it comes. So first of all, to there is a, how should I say, uh, there is a general heat conduction equation, which is nothing but, you must have seen it, but I'll just summarize it here and then we'll go to problem solving. So since we are dealing here with the steady state, or I should just write as the general heat conduction equation. So this will be 1 by alpha partial derivative of temperature with respect to time equal to, this is a 3D form of the equation, so xyz, and since we are talking about planar walls, we'll take the Cartesian coordinate system in xyz coordinate, and this will be your I think heat flux and or heat source, sorry, not heat flux, it should be volumetric heat source, and K is thermal conductivity. And there are a lot of things about this equation, but first of all, we'll just simplify this. There are different cases. So in this equation, if the heat generation term is 0, then the equation simplifies. You can just copy these terms. So we'll get equation of this form. So only this q dot by k term goes to 0, and this is called as diffusion equation. I'm telling this because in one of the competitive exams, they directly ask the term like diffusion equation or Poisson equation. So if you don't know, then you can't do anything there. So maybe you can keep in mind that these small modifications, actually this changes the nature of the PD that is to be solved, and that's why different categories are there. Then if it's a steady state, sorry, if steady state is there, then this del t by del t term goes to 0, and you'll only have the terms on the RHS. So basically you'll have this whole thing, and that will go to 0 because there is no unsteady term on the other side, and this is called as Poisson's equation. And then there is last variation, which is called as steady state plus q dot equal to 0. So this is the further simplified case, and in that case only this second order terms will be there because q dot will also go to 0 from this equation, and then you'll have just the second order terms equal to 0, and this is nothing but called as Laplace equation. So these three things are there. They are not usually told, but in some competitive exams they directly give that solve the Laplace equation for heat conduction, etc. And at that time, if you don't know, then you'll get stuck. And sometimes this is shown in a concise form as this Laplace operator is there. If you are not aware about it, it's fine. You can remember the whole thing. Otherwise, there is a concise way to write this Laplace operator using a Laplace operator. And keep in mind, these are for planar slabs. I mean, this is not true for all cases of conduction. For cylindrical and spherical, there will be different equations. More or less, it will be similar only, but it's just that because of the change of coordinate system, the Laplace equation or the Laplace term changes its form. Other than that, there is not a major change. You must have gone through the energy balance equation derivation in the class. So that was done for Cartesian coordinate system. So when it comes to cylindrical or spherical system, similar equations or similar derivation is there, and you get the respective conduction equations for those geometries. So this is the main thing that you should be aware of. And after that, we'll keep the cylindrical and spherical things later. And heat generation also, I think next week it is discussed in the plane slabs itself. Then slight discussion on the and there is this, I mean, typically what they call, and here today we'll be mostly dealing with 1D steady state heat conduction. So keep that in mind. And other than that, there is something called as Fourier's law. So these two laws will be basically they are fundamental blocks. So when you solve some examples for conduction, the governing Fourier's law is governing law for conduction, and it is typically the flux is equated with some proportionality constant which is called as thermal conductivity, and then temperature gradient. So temperature gradient in basically you can write grad T as del T by del X, uh, you know, I cap plus del T by del Y J cap plus del T by del Z K cap. So this is like the 3D form of grad T. But if we are dealing with 1D equations, then for 1D this simplifies as heat flux in that direction, let's say X direction, is negative of thermal conductivity in that direction, and then it becomes only function of dx. So basically it becomes OD, or ordinary differential equation, and generally we assume that K will be, you know, isotropic, and so that means it will be same in all three directions x, y, z, and then we just take it as K. There are different problems in which K also has some variation, but typically this is there. And this negative sign is very important. Sometimes people forget this sign. Uh, so basically when you solve the problems, it's okay because you compare the numbers. But if you want to understand what it means, then you should never forget this negative sign. So what it means is positive direction of heat flow, which is denoted by this flux term, will be opposite to the positive direction of temperature decrease. So what it means is, essentially it means uh, heat will always flow from or I should rewrite flow in the opposite direction to that of positive temperature gradient. So uh, if you take it in the other sense, it means uh, I mean this is equivalent to saying that heat will always flow from uh, high temperature to low temperature, and this is nothing but direction of decreasing delta T. So this is just a fancy way of saying the things that uh, the heat transfer or the conduction, heat transfer due to conduction will always happen if there is delta T between any two points, and that delta T should decrease. Then only heat will flow from that direction to higher temperature to lower temperature in that direction. So that's why this negative sign is important. So keep that in mind. And similarly, for we'll deal with some uh, you know convection cases also. So there, Newton's law of heating or cooling is the governing equation for convection. Okay, and again it is similarly convection flux will be function of some constant which is typically called as heat transfer coefficient, and delta T. So here it's not grad T, okay. This triangle is like normal triangle. In the conduction Fourier's law, it is inverted triangle, which is gradient symbol. So yeah, and one more thing that you should know, that K, which is thermal conductivity in case of Fourier's law, is a material property, whereas H in the Newton's law of heating or cooling for convection heat transfer is not only function of uh, fluid properties or material properties, but it also depends on other properties such as surface roughness, flow velocity, etc., etc. So this H, heat transfer coefficient, is very broad term. We'll discuss about it later, but for now, keep those distinguished differences in mind. Now, oh sorry. Now coming back to the conduction thing. Uh, okay, about thermal conductivity. Typically, it is denoted by small k. This is general notation for thermal conductivity. And first of all, its units, SI units. Sometimes these simple questions are asked, and I have seen that people don't know. So for SI units, maybe you can derive from its normal units, which are watt per meter Kelvin. And we know what is joule per second. So it will be joule per second per meter per Kelvin. Now joule is nothing but energy unit, which is force into displacement. So force is Newton and displacement in meter, and the second meter Kelvin remains like that. Mm will go, it will get cancelled. So basically you have Newton per second Kelvin. Newton is force into, Newton is unit of force. Force is mass into acceleration. So by that logic, it will be kg is mass, acceleration is meter per second square, divided by second and Kelvin. So further simplify, if you do, you get kg meter second power minus 3 and Kelvin. So in terms of this MLT system, if you want to write dimensions, there will be M1, L1, T minus 3, and theta will be there. Theta is temperature, so that Kelvin will come in terms of theta. So this is also asked many times, and you should be aware of these things. 1 second. Then there is one more thing that we missed, which is at the start only, in that governing equation case. 1 second. Let me just confirm this. Oh, sorry, this will be -1 because it is in the denominator. Okay. Now we missed one more thing, that is given as thermal diffusivity, which is denoted by alpha usually, and it is associated with this del T by del T term. Okay. Then about thermal diffusivity, its formula is, you must be knowing from class, it is K by rho Cp, and it represents, see, basically K represents the tendency of the material to conduct the heat, and rho Cp, it is mCp per volume. So mCp delta T essentially is the amount, or the what you call the inclination of that material to store the heat. So therefore usually they call it as alpha or thermal diffusivity. It's not a formula, but it's a concise way to define it. Ability of material to conduct heat through it, and divided by ability of material to store heat within it. Thermal diffusivity becomes important in many applications, such as quenching of metals, etc. We'll discuss this later also. It will come again, but for the timing, you should know this. And coming back to the dimensions of it, it will be always meter square per second. Any diffusivity that you see in any literature. So here it is thermal diffusivity. Later there will be one kinematic diffusivity. In case of electrical problems, there is electrical diffusivity. Then what? Mass diffusivity is also there in Fick's law. All diffusivities, they'll have same unit of meter square per second, and no kg or mass dependence. So these are small things. You should keep them in mind. So meter square is L power 2 minus 1. So this will be true for all diffusivities. In many competitive exams I've seen, they just give you some random diffusivity and they ask the unit. So if I ask you electrical diffusivity unit, you can't derive it that easily unless or until you are from electrical background and you know some relationship in which that term comes. But other than that, if you are from mechanical or some other background and if you don't have that much electrical governing equation knowledge, you'll be stuck. So you should know this trick that all diffusivities will have same units, meter square per second. Okay. So yeah, I think basic stuff we have discussed so far. Okay. I don't know what is happening here because I started with one second. What is happening here? Where did that thing go? Yeah, here. Okay, I think there was some software glitch. First slide was coming again on fourth page. Okay, so now it's not there. So now we'll start some problems. But before that, you should know that today we'll focus on simplified heat conduction problems and what all simplifications are there. Steady state, no heat generation, and it will be planar geometries. So that means like brick, wall, something like that. So in that case, and yeah, 1D, so one dimensional problem. So typically we'll consider it as x direction and will not write x everywhere. Uh, that is understood. So in that case, what your problem becomes is your heat flux will be as per the Fourier's law. It will be function of conductivity and what you call this x direction if you are considering your 1D direction as x. Now heat flux is nothing but heat transfer rate divided by area. So from there you get heat transfer rate as minus Ka dt by dx, and in case of planar geometries, something like this. Typically, you know the thickness, which is called, let's say, B, and you'll know some T1 temperature and T2 temperature. So the dt by dx simplifies further as T2 minus T1 divided by B, because this is your x coordinate. So that gradient is basically delta t by d. So if you put that in that q dot formula, so you get minus ka delta t by d. And if you rearrange the terms, you get minus delta t by d by ka. And keep in mind that this a is the cross-sectional area perpendicular to heat flow direction. I have seen students getting confused in that A term also. So keep in that mind. So in this case, the heat will be flowing from here, and this if you expand this slab in some third dimension like that, so it will look something like this, and you know, this is your A because it is perpendicular to the direction of heat flow, and this is your heat flow direction. So like that. And then they use electrical analogy because most of us have studied those things in our previous education, that and yeah, and how they do that, uh, there is actually one previous year question on this. Let me just, yeah, so this was, I think, ESE question. So you have list 1 and list 2, and you had to match the pair. So this is the question. Actually, yeah, I'll write QU because otherwise you may get confused between heat and question wala symbol. So here you have voltage, current, resistance, and you have capacitance. And then on the other side you have, let's say, one thermal resistance, thermal capacity, heat flow, and temperature. So you had to find the correct pairings. So this was the question. So typically in an electrical network, there will be some voltage source, there will be some resistance in the circuit, and it will be closed circuit like this. Let's say this will be a positive flow direction, this will be a resistance, and the current will flow. So typically what they do, they imagine the same thing here for, and here you will have temperature difference. That temperature difference will drive the heat flow rate, and this will be thermal resistance, and it will always flow from positive to negative. So you have to use this analogy actually, and okay, so by that logic, the correct pairing will be, voltage is nothing but equal to temperature, so A4, current is equal to the heat flow, equivalent to the heat flow, B3, resistance and thermal resistance, so C1. Yeah, and capacitance, it is not shown in this small circuit diagram, but you can imagine there will be capacitance in uh, electrical network, and that role is played by thermal capacity, which is nothing but function of you know, if you want to do that, it will be function of rho Cp, something like that. For this problem, it will be D2. So this will be your answer. So this is your answer. Okay, so such questions are also asked. Then you'll So this is your electrical analogy. So basically, you know that in series the resistances are added, in parallel they are inversely added, or harmonically as they call it. So yeah, we'll take some questions, but before that, uh, hmm, okay, there is a simple question. Uh, Heat transfer takes place according to, first option is first law of thermodynamics. I use TD as the symbol for thermodynamics. Second option is second law of thermodynamics. Third is third law of thermodynamics. And fourth option is there is no fourth law of thermodynamics. Okay. So zeroth law of thermodynamics. So those who have done thermodynamics before this course, they should be able to answer this question. If you have not, then the correct answer is basically the second option, because second law defines the concept of something called as entropy, and heat transfer always takes place, or heat conduction at least, always takes place in the direction of decreasing entropy. So uh, you know that not only heat conduction, many physical phenomena are governed by second law of thermodynamics only, due to concept of entropy. If you have not studied thermodynamics, you will understand more when you study it, because we cannot discuss that here, because it will be too much digression. And if you have studied thermodynamics, you should know that entropy dictates mostly everything. Okay, so that was one of the simple question that was there. Then we start with something simple. For example, what should I start with? Hmm. Okay, so okay, so there is slightly, I mean, this problem has, it's not that difficult. It just has some, trick. So basically, there is a slab of, there is a rectangular of this slab of steel, and the thickness is 5 centimeter, and on one face there is a flux of 800 watt per meter square. This is face A, and thermal conductivity of steel is given as 20 watt per meter square Kelvin. And there is other side of this slab, which is surface B, and it transfers this incoming heat from the surface A to an environment which is at ambient temperature of 25 degrees Celsius with heat transfer coefficient of 80 watt per meter square Kelvin. Then we need to find temperature of surface B. This is the question. So Now, here we have to use the concept of thermal resistance network, and it's like this electrical analogy only. So what you do is you represent the thermal network in terms of resistances. So basically, you'll have this point A, then there will be conduction resistance till point B, and after point B, there will be, let's say, some point C in the ambient where you have T infinity of 25 degrees Celsius, and this will be your convective resistance, which is 1 by HA, and here it will be conduction resistance of the steel slab, that will be B by Ka. But in this question they have not given you area, right? So but instead they have given you heat flux, which is 800 watt per meter square, and area is same for conduction and convection heat transfer, right? So what you can do, you can directly multiply this flux into some area, and then you can write the energy balance. And what will be your total resistance? Since this is these are in series, it will be B by Ka plus 1 by Ha. Take this area outside because that's an unknown. So B by K, B is 5 centimeter, so that will be power minus 2 in meters. K will be 20 plus 1 by H is given as 80. Okay, so if you do that calculation, you'll get some number here. But the question is, what is asked in the question? They are asking what is the temperature at surface B. So we don't need to do this also. I just explained it because you should have the idea as to how to proceed with this type of problems. But here you have a simple trick. You just consider B to C thermal network. So if you do that, what you can see is this, you know, the flux that is coming, it will be same only because it's a steady state problem. So same flux will go from A to B and B to C. That will be nothing but equal to, according to Newton's law of cooling, H into surface temperature of TB minus TC. And directly from here you get the answer. So that will be 800 and it is 80. TB is unknown and TC is 25. So therefore TB becomes 35 degrees. So in this question, they gave you all this slab web, etc., to confuse you. They could have directly given you this H and delta T infinity, and directly you could have gotten it. But sometimes they do in some competitive exams, especially in prelims or something like that. They'll give you a lengthy question, but in the end you'll realize that this much was not needed actually. But anyway, that is how it is. Then we'll do some, you know, uh, some tricky problems, because straightforward problems you'll do anyway. One second, I had seen the problem. Okay, so we'll go line by line. We don't need to be in a hurry. There is actually one very common problem that is asked almost multiple times. We'll go to that. Let me just confirm. Yeah. So it goes something like this. They'll tell you that there are two slabs. Okay. And they are of equal thickness but different material. So one will be made up of K1 thermal conductivity, another will be made up of some K2 thermal conductivity, but they will be of same. Okay, they will be of same thickness, which is nothing but B, and there will be some heat transfer from some this flux, something like that, and they will ask uh, for equal thickness of two layers equivalent conductivity of the slab will be. So basically what they are saying is, if you replace this slab uh, with same thickness, but uniform material, so this will be 2B now, because you are replacing with same thickness, but there will be some material which will be having K equivalent conductivity, so that you will have same flux through the wall. So in that case, what you have to do is basically uh, for this wall, your thermal network will be something like this. The central node will be your interface, and for first slab the thermal resistance will be K1 by B, sorry, B by K1 into some area A, and here it will be same thickness, so B, but K2 into A. And for this type of arrangement, because this has to be equivalent, you will have a common or single resistance between or same flux, and you'll have thickness will be 2B, because the same thickness you have to keep, and some K equivalent into area. So uh, now, and this delta T will be obviously same, otherwise you can't compare this way, right? So there will be something like T1, T2, and same temperature difference should exist between these different K equivalent slab also. So if you do that, what you'll realize is, you know, so basically your, let's say, this B by K1 A plus B by K2 A will be your resistance for first thermal case, and second case will have the resistance something like K equivalent into A. So AA cancels, and you'll end up with K equivalent as, actually BB also cancels. So it's essentially 2 by K equivalent is 1 by K1, so like that. And if you simplify, you'll get 2 K1 K2 divided by K1 plus K2. This will be your equivalent thermal conductivity, and this is your answer. So this is actually a very commonly asked question in many competitive exams. Okay. Apart from that, what else? Yeah, so one more type of trick question is, so far what we did, we assumed that your thermal conductivity will be constant, right? But it can change, not with respect to uh, x direction, but with respect to temperature. Thermal conductivity in real case changes. Generally we assume it won't change, but in reality it does. So let's say in one of the question, the temperature distribution along a slab is given like this, and no heat generation, and they have mentioned that the question is, the thermal conductivity K will vary as, and you have 4 options. Some K naught constant, 1 plus alpha T. Alpha is positive constant, alpha is greater than 0. Or maybe, okay, 1 second, I'll clarify about alpha, but let's write down the options first. 1 minus alpha T. Then there will be K0 plus alpha T. Fourth is K0 minus alpha T. So something like that options are there. So, if you see this problem in competitive exams and if you don't know, then you'll spend a lot of time on this. So therefore, see here what is happening. The T1 is greater than T2. That is visible from the figure. And T1 actually there, like T1 will be maximum temperature in the whole slab because there is no heat generation. If there is heat generation, there can be any point in the slab where the temperature can be greater than T1. That we'll see later in the next class maybe. But here, see, so far, let's say if K is equal to some K naught, which is constant, then we know that we'll end up with some straight line. So T1 is equal to T2, and because it is not function of temperature, it's just a constant. And how do you get that? Because of the uh, Fourier's law. That's what we assumed also initially, right? Here, there it is. Here T1, T2. So in this case, if K is constant, it will be like this, straight line. And so basically here, your K is function of temperature, and like how should I put it? Mm, hmm. Okay, so let's take our general flux is minus K into okay, actually there is one more question that is coming to my mind right now, but we'll discuss that later. So here in our given question in this one second, where is that? So in this figure, sorry. So in this figure, uh, you know, temperature is not linear. So K is function of temperature, something we don't know, but the shape you can see is convex. Anyway, so T1, let's say T1 is greater than T2, right? So T2 minus T1 will be less than 0, negative. So that means dt by dx is less than 0 because your temperature with respect to x is decreasing. So its change will be decreasing. So in this case, and Q star, this term will be always positive because it's a heat. So what happens? If dt by dx is negative, then there is always negative side there. Therefore, if dt by dx is negative, k, k will increase with x. So you have to do analogy like that. So okay, so T2 minus T1 is negative, 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 positive. So your K will be increasing. with respect to x. And when does that happen? Or with respect to t also, because, oh, 1 second, and t is decreasing with x. So these two informations here. So based on that, yeah, and if alpha is positive, one second. Yeah, so in these options, if we consider alpha as positive, let's say it is not given, so the alpha can be positive or negative, right? So your t is decreasing with x, your k should increase with x, so that you'll have q dash as positive. So if alpha is greater than 0, t is decreasing with respect to x. So by that logic, your k should be equal to one second. In this case, actually, they have not mentioned this alpha. Therefore, these options A can also be correct and B can also be correct depending on alpha. So to avoid that confusion, let me just check. Yeah, so basically what happens if alpha is greater than 0, so that is positive, and when you march with respect to temperature is decreasing, so your k naught, this k naught plus some term is decreasing, so your k naught should decrease, right? One second. So the thing is, I know the answer, but this logic is not happening. The answer is, which is, I mean, corroborated from multiple sources. So typically what happens, in such problems, like you can remember this figure. So this will be our case, and then there is second case like this, and then there is third case like this. So here alpha will be greater than 0, and your k will be k naught into 1 plus alpha t. So depending on alpha, you'll get three solutions. Alpha will be 0 here, and alpha will be less than 0 here. This is actually like very common problem, but the logic, one second, and this will be the direction of heat flow. So yeah, I mean, here the solution is first option, but the reasoning, let me just think on it for a minute or so. Actually, there is one more question, similar question. So in that question, what they asked is, so here so they are asking k as a function of some k naught plus 1 plus alpha t, right? There they asked about k and dt by dx. So I mean, multiple type of questions can be framed, but let's not go there. Mm. Yeah, see, with respect to x, so we are correct that t is decreasing with respect to x, which is given. So to compensate for decrease in t, k has to increase with x. But what about k with t? That is the question, right? Because this is as k naught into 1 plus alpha t. The reasoning should be quite straightforward, but I don't know what's missing here. Maybe I can revisit it later. For now, we can go ahead. Okay, so see, t is decreasing, so alpha t term will be negative. So 1 minus alpha t, it will be decreasing. So if you multiply that, k naught is decreasing actually. Okay, I'll come back to this maybe if we have the time at the end, but the correct solution is this k naught 1 plus alpha t only. Is there any other way so that I can check it? Yeah, so that's what I'm saying. If alpha is less than 0, then second option also is same only. So this question is thoda confusing, but this is the correct one. So you remember this part. So if alpha is greater than 0, it will be convex, and alpha is less than 0, it will be concave. Okay, so we'll come back to this later maybe, but right now we are running out of time, so let's go to some other questions. There is this question also. I mean, it's not that difficult, but sometimes they confuse you with the language. So what they are saying is, for a plane composite wall of n layers given by thickness Ti for ith layer, thermal conductivity Ki for that ith layer and convective heat transfer coefficients H1 and Hn on first and nth layer. What will be the overall heat transfer coefficient U. And they have mentioned that yeah, I mean that's it. So basically there is a composite wall. So there like so composite wall will have multiple slabs like this, right? So there will be one more slab like this, and there are like n slabs. Right. So this will be your first slab, this is second, and this is your nth slab. And each one will have conductivity of K1, K2, Kn, thickness of T1, T2 till Tn. This I is your index which goes from 1 to n. So and your here there is a convective heat transfer coefficient of H1. From here there will be one resistance, right? And here there is one more resistance and there is Hn. And then there are like, let's say, two temperatures across those T1, T2. So now you know the concept of, you know, and yeah, they have not explicitly mentioned, but the cross-sectional area is same. Cross-sectional area for all slabs is same. So you know that concept of overall heat transfer coefficient, that if you consider the flux, this is overall heat transfer, it will be T1 minus T2. So basically now we have to do the TRN. But here one thing is there. So if you consider first slab and if you consider its thermal layer, it will be T1 by K1 into A. Similarly for next slab it will be T2 by K2 into A. So you can indexize their resistances also. So what I mean is R total. So first you'll have 1 by H1 A plus T1 by K1A plus T2 by K2A, and in the end you'll have Tn by Kn into A, and one last 1 by Hn into A. But you can shorten this whole thing something like this: H1A plus, you can put summation sign and you can use index I1 to n, and it will be Ti by Ki into A plus 1 by Hn into A. That's it. So if by this logic, if you write Q flux as and you can take A common, then it becomes this whole term, you know, this whole term, because this is resistance, so it will come in the denominator. So maybe we should write it that way. So it will be here somewhere. Yeah. So it will look, because delta T by R total is there, right? So and at the top there will be T1 minus T2 delta T. So you can do one thing, you can take this won't be Q dash, it will be total Q. So you take the area common, and if you divide it by area, so that A term will go away, and from 1 and 2 if you compare, you get U as a this whole denominator term and inverse of it. So because it's inverse term, so here will be 1. Index is n. So this is it. We'll use this similar concept in heat exchangers also, uh, where you basically neglect the thermal resistance because typically it's not that significant. But okay, anyway. So yeah, this is so if you directly see this type of expression somewhere in uh, problems, don't be afraid. It's just a concise way of writing bigger expressions. Moving on. Uh, yeah, there is one easy problem also. There actually it was dt by dt. This one. So here they have given. We'll take next question. So here it is mentioned that for a large concrete slab of 1 meter thickness, the temperature distribution is given as 4 minus 10x plus 20x square plus 10x cube. The T is temperature and x is different, distance from one phase to the other phase. Thermal diffusivity for the concrete is given as 2 into 10 to the power minus 3 meter square per hour, and asked what is the rate of change of temperature at other wall. So by other means at x equal to 1 meter. Uh, so now this question is slightly different because here you have temperature distribution, and what they are asking is what is the rate of change of temperature at the other face of the wall, and in degrees Celsius per hour. So they have given unit also in which you have to answer. So by unit only you will get the hint that they are asking for del T by del T. So we are digressing, we are not taking steady problem, this is unsteady problem, and that is why this alpha is given. So in steady problem they'll only give you conductivity. Alpha comes, that means there is some role of time, then only alpha is required. So from our earlier equations we know that 1 by alpha del T by del T will be del square T by del x square. Here there is no heat generation and only 1D heat conduction we are studying. So therefore this will be our equation, governing equation. You can go back and check. So now we need this term. We have T as 4 minus 10x plus 20x square plus 10x cube. So we can differentiate it with respect to x. That will be minus 10 plus 40x plus 30x square. Again we have to take one more differentiation. That will be 40 plus 60x, and if you calculate it at x equal to 1, which is what they have asked, this will become 100. Okay, and the unit will be degrees Celsius per meter square. Now put that in the governing equation. So then del T by del T will be alpha into del square T by del x square at x equal to 1. Alpha is given as 2 into 10 to the power minus 3 meter square per hour and into 100, and the unit will come to be degree Celsius per hour. So if you do that, you get 0.2 degree Celsius per hour. So the question sometimes look uh, very difficult, but if you know the basics, you will be able to solve them, is what I'm trying to say. Yeah, like that. Then what else? Yeah, there is one more question which I had saw. So basically, what they are saying is one cube is there, I think. Yeah, something like that. H1, H2, H3. Yeah. So this is also, but this is not a conduction question actually. So we'll leave it. This is convection. Maybe we can take it up later. We'll take some other question, interesting ones. So yeah, there is one question in which okay. So now see, there are like multiple tricks that can be done. What I can do is I can give you, or what I mean, rather than saying, I'll give you a problem directly. So okay, so in question they have mentioned that there is a steel slab like this, and there is a heat flow across it. It's a flux only. Let's say Q1 dash W dash. This temperature is TH, this is TC, and thickness is L. This is made up of steel. Okay, so this is the initial case. Then what they did, this steel slab is as it is, which it was earlier. L TH will be same, but now there is Q2 flux flowing through it, and they have attached one more. This is steel slab as it is, and of equal length they have attached a copper slab, but they have kept the outer temperature as TC, and this temperature will be some TI. Okay, now what they're asking is whether or so you have to check whether Ti is equal to Th plus Tc by 2. That is first question. And whether Q1 is equal to Q2. So basically the flux is same or not. So this is actually like one of the difficult questions. I think this is previous year GATE question, older ones. So now here one may get overwhelmed with the scarcity of information that is not given in the question, but it's not that difficult actually, to be honest with you. What you have to do, first step is in this type of problems, just draw the thermal network resistance. So for first case, you have TH, TC, Q1 double dash, and we'll take, you know, we'll take Ks as the steel conductivity and Kc as the Kc as the copper conductivity. So here your R1 will be L by Ks into area. And in another case, here it is TH and TC. So these are same. There is Ti which is unknown, and your flux Q double 2 double dash is also there. And here the resistance will be again L by Ks into A. Here L is same, but K is changing, right? So Kc. And since we are talking in terms of fluxes, we can neglect the area terms here itself. Otherwise, anyway, in the end they get cancelled. So here R2 will be summation of L by Ks plus L by Kc. If you take L common, these are 1 by Ks plus 1 by Kc, right? So we know that thermal conductivity cannot be negative, right? So Kc will be always greater than 0, and it will be very high than steel actually. Copper is, I mean, at least 10 times more conductive than the steel. So therefore, 1 by Kc will always be greater than 0. And by this logic, R1 will be less than R2. Because in R1 only L by Ks is there. In R2, there is 1 by Kc term is also there. Therefore, R2, matlab, thermal resistance in the second case will be higher than the first case. And therefore, what happens? Now you have some clue to go on, right? Because before this, so it was all no idea. And here the trick is this TH and TC are same, right? So therefore, uh, what works in our favor is we can write Q1 dash as TH minus TC divided by R1, and here Q2 double dash is TH minus TC divided by R2. So since R2 is greater than R1, Q2 double dash will be less than Q1 dash. So now you got your half part of your question answered. So this is the important thing. So that means they are not equal. So this claim is wrong. Now about the Ti. So how to get about it? So okay, what you can do here is Ti comes in only second part, right? So you can't use first part. So let's go to the second part. So we know that Q2 dash, sorry, Q2 double dash is as given here TH minus TC by R2, right? But we also know that TH minus TI divided by L by Ks, and that will be same by Ti minus Tc divided by L by Kc. This is from the thermal network. So we can use these two terms. So what happens here? LL gets cancelled. So basically you are remained with Ks into Th minus Ti will be equal to Kc into Ti minus Tc. So now we have some relation between I, H and C temperatures, including thermal conductivities. So now we have to simplify. Now to do that, you can simplify. Okay, you can take the ratio. So let's say Kc by Ks. If you take that, it will be Th minus Ti divided by Ti minus Tc. Correct? And we know Kc is greater than Ks. Therefore, Kc by Ks is greater than 1. This ratio will be greater than 1, and therefore Th minus Ti divided by Ti minus Tc will be greater than 1, and therefore Th minus Ti will be greater than Ti minus Tc, and that implies Th plus Tc will be greater than 2Ti, and therefore Ti will be lesser than Th plus Tc by 2. So this is your second answer. Okay, so basically both the claims are wrong. This claim is also wrong. So like that, many type of questions can be framed. This topic looks simple, but interesting questions are there. Then there is one more. Uh, since we are talking about composite walls, one second. Yeah. So since we are on the topic of composite walls, this type of questions are also asked. So till now we had same area walls in series, but sometimes they give you something like this. So there will be wall here with K1 and thickness will be something like B1. Then there will be some wall, another wall with different material of K2. Then there will be K3, and they'll have some, this will be your A1, A2, and this will be your total area, which will be A1 plus A2, right? So in such cases, they will, in question it will be given that you'll have some. In this case, they cannot give you flux because area is also changing, right? So they have to give you uh, Q, or the heat transfer rate, Q dot. So that will be like this. This will be something P2 equal to P3, because for second and third material the width are same but area is different. So this type of complicated structure of composite walls is also possible, and it is asked also many times. So here also you don't need to worry, you just have to divide everything. So there will be one resistance from main or the bigger material slab. Then there are two slabs in parallel. So you'll have something like this. And then you'll have some node temperature. So if this is T1 at the face and T2 at the here, so this will be T1, this will be T2. Actually, T2 will be, strictly speaking, T2 will be here itself. So like that. So now you know how to calculate, or you can extend it slightly since there is no other network or resistance. So this one, it will be K1 by B1 into A1 plus A2, right? This will be its R1. R2 will be K2 divided by B2 into A1. Okay, maybe we should change the notation, otherwise it will be A2 and A3. So this will be A2 and A3. So yeah, A2, A3. This will be A2 and R3 will become K3 B3 into A3. And B2 and B3 are same, so you can use same symbol for any one of them. And before complicating everything, you can do simple thing like R total, and that will be R1 plus R2 R3 divided by R2 plus R3, because R2 and R3 are in parallel and their resultant is in series with R1, so it will be like this. Now you have R1, R2, R3, right? In some of the questions they will give you this all the values instead of symbols here, but you get the point, right? So now Q dot will be T1 minus T2 by R total. So this question can be framed in multiple ways. So I will give you some correlation between A1, A2, A3, K1, K2, K3, something like that. So, but the general theme remains same. You have to draw the TRN, thermal resistance network, and you have to solve. Then what else? Let me see, because there are like many problems which are, you know, uh, not like slab, they are like cylindrical also, so we'll take those later. But before that, yeah, simple problem like this is also asked many times in especially competitive exams. So they will give you two walls, composite wall, something like this, and there is some heat flowing through those. This wall is at T1 and this will be made up of K1 conductivity, and there is another wall, this will be a T2 and this is made up of K2 thermal conductivity. And simply they will ask uh, K1 is greater than K2, which of the following is or are true. I mean, it can be multiple choice question also, depending on the exam that you are preparing for. So K1 greater than K2, second option K2 greater than K1, third option K1, K2 are equal, fourth option uh, something random, K1 is 0.5 times K2, something like that, or none of the above is also there many times. So in that case, here basically you have to understand, let's say if Ti is interfacial temperature, which is not given in the question, but you can start thinking in this way. So from figure we know that Ti, or sorry, T1 minus Ti, this delta T is less than Ti minus T2. That is clear from the figure, right? So we know that it's a steady state problem, so Q dot will be same flowing through both the walls, and Q dot is nothing but the product of K1 K into delta T, because these walls will have same thickness also, let's say some B thickness, so that B by K term, A is same, B is same, so only it boils down to K. So we know that Q dot will have K1 into T1 minus Ti, and some B and A term will also be there, equal to K2 into Ti minus T2 into some area term and B. So this is from our resistance network. I have not drawn the resistances, but you get the idea. We have done so multiple times. So these won't come into picture while comparison. So from here we can again take, you know, uh, since this first bracket is less than the second bracket has K2 has to be greater than 1, right? Then only this equality will hold. Otherwise, equality won't hold. So this is your answer. But more than that, what I feel is, one second. Have I made any mistake in this? Ulta. K2 will erase. Yeah. I mean, see, uh, this term is lesser than this term. So this K2 should be less than K1, right? I just wrote it in the wrong sense. So K1 will be greater than K2. Then only this equality will hold. So this is the mathematical way. But, okay, so I have to... sorry. Yeah, K1 is greater than K2. And more than that, mathematics aside, what happens? See, uh, if if there is a metal and if it is conducting heat, so it will conduct heat with lesser temperature drop because it has higher thermal conductivity, and that's what we call conductor or superconductor for that matter. Uh, but if there is some insulator, let's say like nitrile rubber or glass wool or normal wool also, or wood, they are thermal insulators. So if some heat is flowing through them, there will be significant temperature drop. That's what insulator does, right? And therefore they will have to have low K. So typically K of copper will be very much higher than K of wood, and therefore delta T across copper will be very small as compared to delta T across wood for same heat transfer rate. And that's how you need to solve these type of questions. You need not always do the maths. If this straightforward question is there, wherever you have more temperature drop, their thermal conductivity is less, is what is the conclusion. So this type of questions are very common. Other than that, let me see. Yeah, this was also one of the questions. I mean, very thought-provoking questions are asked from these topics. Many people think conduction is the easiest of heat transfer. It may be, but it can be tricky as well. So, so let me just see. Yeah, this was the gate question actually. I think I touched upon it. So basically, in this part, yeah, this part. So there they had mentioned that K is equal to K naught 1 plus alpha T, and alpha is greater than 1. And in that case, what happens to the dt by dx as x increases? So this is straightforward because as x increases, t increases, then k also increases, that is k is positive. 1 second. Yeah, I'll solve that question so that we'll go away with the confusion in the previous one also. So in that question, what is mentioned is there is a slab like this, and one temperature is T1, another is T2, and it is given that T2 is greater than T1. This is your x coordinate starting from here, this one. Given is k is equal to k naught 1 plus bt, or okay, they have given k naught as k naught plus bt, a linear function of temperature, where k naught and b are positive numbers or constants, not numbers necessarily. So your k is a positive function of t, and it is asked that there is no heat generation, etc. Question is, as x increases, dt by dx will, first option, constant, second option increases, third option decreases, fourth options 0, like that. I mean, I've abbreviated the options because it takes time to write, but you get the idea, right? So here in the question it is mentioned that T1 is greater than T2, so it will be something like this, and this will be your T2, so like this. No, uh, direction I should not say here because it cannot flow from lower to higher direction, so it will be like this only somewhere. Yeah, so now see what happens from figure. As x increases, I'm using up arrow for increases, so as this x increases, t is decreasing. Oh, I'm sorry, t is increasing because t2 is greater than t1. Okay, and from equation 1, which is, let's say, this one, as t increases, k also increases because they are positively correlated, right? That is what is given by equation 1. And as k increases, we know that from Fourier's law, for same heat rate, as k increases, dt by dx should decrease, otherwise it won't be in steady state, right? So therefore this is your answer. Yeah, so coming back to that previous question where I was slightly confused, I got confused because of this sign. So typically, I mean, for comparison, this sign cannot be like, it should not be considered, is what I feel. Anyway, so the thing is, yeah, so here what was given, that T1 is greater than T2, and let's say this is again your x coordinate, and as x increases, T decreases. Yeah, so T decreases with uh, x increase, and the T decreasing, that means dt by dx is decreasing. As x increases, T decreases, so dt by dx decreases. So that is what dt by dx less than 0 implies. And if dt by dx is decreasing, k need to increase. So this is also correct. But k is increasing with x, t is decreasing with x. Again, we are stuck at the point what happens between k and t with respect to x. I mean, which rate is more? That is the question, right? Yeah, so I think in this question it is not, like, the information is not completely given. Maybe I'll think about this later, but the thinking should be on this line only, because otherwise it won't make sense. Hmm. Yeah, k needs to increase with x because t is decreasing with x, right? Otherwise, q prime flux won't be same. But how much? Because it should be decreasing in the same manner as t is, sorry, it should increase in the same ratio as t is decreasing. But then how can we convey that information from here? See, if alpha is negative, then option 2 will be correct by that logic. And let's say alpha is positive, then 1 and 3. What is the difference between 1 and 3? That is the question. I think in this question there is scarcity of information or something is missing. That's why the confusion is coming. But this question is fairly, uh, you know, informative. So yeah, so basically you have to see with respect to x whether temperature is increasing. If it is, then your dt by dx becomes positive, then your k has to decrease. In this case, with respect to x, your temperature is increasing, so dt by dx is positive. Oh, sorry. Uh, with respect to temperature, with respect to x, temperature is increasing. And as the, oh, acha, okay. Yeah, I think I got my mistake. Yeah, so here the logic, I think, is wrong. We are coming from both the sides. So maybe that's why we are not getting coherent argument. So we'll follow the same logic as we did in the last question. So here, as x increases, t is decreasing, correct? So, acha nahi. Yeah, there it was given, k relation was given, here it is asked. So earlier line is also correct only, line of thinking. Anyway, we'll wrap it up. Temperature is decreasing with respect to x. That means dt by dx is decreasing, and to maintain uh, same flux, k has to increase. Correct, otherwise flux will not be same and it is not a steady state then. Now k has to increase, temperature has to decrease, and that is happening. And let's say alpha is greater than 0 is given. So in that case, k has to increase, t has to decrease. So if t is decreasing, alpha t term is k has to increase, right? If t is decreasing with respect to x, alpha is positive, so alpha t term will decrease. So that will, okay, so now I got the point. Okay, so as x increases, t is decreasing, same thought. Therefore, alpha t is also decreasing because alpha is positive now. And alpha t is decreasing and k needs to increase. Yeah, since alpha is positive, alpha t also is decreasing with respect to x. And k has to increase with respect to x. So that is possible only when so that is possible. So I mean, these both cases are possible in option 2 and 4. I don't think 1 is correct. Maybe I'll check it again later. But see, t needs to decrease and k needs to increase. I mean K has to increase basically. But if alpha is positive, so 1 minus something which is decreasing. Yeah, so alpha t is decreasing, right? So that will increase the K, na? Because let's say 100 minus 1. Yeah, so I mean, I think option possible is 2 and 4. Maybe this question has something missing. I'll go back to it later. But take this as the note, because this is the we just saw there also. So if it is alpha is greater than 0, then it has to be convex. If it is less than 0, it has to be concave. This is for K naught 1 plus alpha t case. I'll go back to that and I'll check also. Okay, so yeah, we are almost at the end of our class. What else is there? Something interesting. Yeah, one question, last question we'll take and we'll stop. This question, it actually touches upon the basic of the heat transfer that we should be aware of. So there is this is a glass, and on top of glass there is water, and this is your, let's say, y-axis. So within the glass conduction is happening, and above the glass in water there is convection. At the surface temperature is 40 degrees Celsius, and at the bulk of water it is 48 degrees Celsius. So water is basically hot and it is giving the heat to glass. K of water is 0.6 watt per meter Kelvin, and K of glass is 1.2 watt per meter Kelvin. Okay. And let's say we take it as 0 coordinate. It is given that the temperature gradient of T with respect to Y in water at interface is 10 to the power 4 Kelvin per meter, and you need to find what is the temperature gradient at interface but in glass. So water side gradient they have given, and they are asking glass side. So water side gradient will be something like this. So this is your dt by dy water, and this is your dt by dy glass. So these two things are different. You should understand that. And second, what is the H in water? So these two things you need to find. So first of all, this is like basic, this thing, that even though there is convection in water, but at the interface there will be conduction first and then there will be advection. We'll discuss this more when we discuss later convection problems. But keep in mind that even though water is flowing at the top of the glass layer, there will be a conduction of heat from liquid water, bulk water. Convection of heat from bulk water to the interface, and at interface there will be conduction in both glass and water. So basically what I mean is, at water glass interface minus K water area dt by dy, let's say water will be equal to minus K glass area dt by dy glass. So there will be conduction on top of glass, on top of glass in water also at very small scale, I mean length scale. So if you simplify this, you get dt by dy of glass as dt by dy of water into K water by K glass. So these things are given, and if you calculate it, you'll get minus 4 Kelvin per meter. And secondly, you need to find H, right? So now you can discuss in water. So conduction, water, heat transfer in water through conduction at interface will be heat transfer due to convection in the bulk water. And this is like at interface. This is in bulk. So same this formula K W A dt by dy of W will be equal to, you can put minus sign here, and I mean that sign you have to take care, okay, because how should I say this, see, we know that bulk temperature will be higher, so if you remove negative sign, you have to take bulk temperature as HA T bulk of water minus T water at interface. So like that. So you need to see that signs won't change. This area gets cancelled, and we know the things. So H will be T bulk is 48 minus 40 interface temperature, and K water is 0.6, and this is 10 to the power 4. So if you calculate those, you get H as 750 watt per meter square Kelvin. Yeah, so like that. Anyway, I think we are almost at 8 o'clock. So we'll stop here, and we'll see the next part of conduction equations in next class. Okay then. Thank you.